finally, in class 3, we're going to get to an example here. Or the other two videos were really just a setup for things in the next class, and then the setup for the re-familiarize yourself with the projectile motion problem. Well, here's an actual example. We have a tennis player serving a ball at a height of 2.5 meters with initial velocity of v naught at an angle of 4 degrees with the horizontal. You can see it's like going downwards though. And determine that we want to find the range at which VO will land in the service area, which extends 6.4 meters beyond the net. Note that the net is 0.914 meters high, and so it has to make it over the net, and it has to stay within this range right there. So we want to find two different velocities. So this is the type of projectile motion problem where we're looking for the initial velocity. There's lots of other ones. The harder type is when we have to find the angle, just so you know. And I'll mention those. Hopefully at the end of the video, I'll try to remind myself that I want to show you the collection of projectile motion problems that you can use to try to test yourself to see if you could work through more complicated ones. But this was fairly straightforward. So one of the first things that I generally will do, if I do know the initial velocity of the thing, is I'll often somewhere write out, do this right away, like figure out what the x component is, and but this is what we're looking to do. So, but we will use this as a substitution. We'll substitute in there. So VO and then the sine of 4 degrees. And by the way, this one should be negative, right? Because he's going down, right? So there's a component. Here's the component there, and here's the component there. This would be V x naught, and this would be this little guy right there. Hard to see him. Didn't do a good job of drawing that in there. And there's V y naught. Okay. And we're going to choose this as the coordinate system. I've already done that for you. We could have picked the origin of the coordinate system up here, but I think it's going to be easier to be here on the ground level, right there. So we want to find the initial velocity to get over the net and the initial velocity to stay in bounds. Those are two things. And this is what we were given as part of the thing. So what we could do is we could say that x1 is equal to 12 point. Okay, so this is going to be x1, right? So this is 0, this is 1, and this is 2. And we already labeled that for ourselves, but if it hadn't been labeled right there, that's what we should probably do if we're thinking through a problem. So the location that we have to here is x1 is equal to 12.2 meters, and y1 is equal to 0.914 meters, right? And I also, I'll write it down below it. I should have written down x first. X naught is equal to 0, y naught is equal to 2.5 meters, right? And then I'll do this one too. So I didn't do them in order, but you get the idea. Is going to be 12.2 plus 6.4, which I believe is 18.6. And so y2 is going to be equal to 0, right? So these are things we're going to plug in to an equation after we get done. So we know that in the x direction, we have x is equal to x naught plus vx naught times t. But for us, that's 0, so it's just going to make our lives a little easier to write this out this way right here, where we have x divided by vx naught, which we happen to know, we happen to be able to put up this stuff inside there. So we have VO cosine 4 degrees. And we could leave this, I could probably leave this as theta for now and then put in the thing later. I don't know why I didn't. Okay. And then in the y direction, and I kind of did this in the previous video, but I'm not sure everyone's going to actually watch that previous video, so I'll do it again. And you need to kind of do this each time yourself. So we know in the y direction we have y naught plus vy naught times t minus 1/2, and you should memorize these things, by the way. But we also have it on an equation sheet, t squared, right? And by substitution, we say y is equal to y naught plus, and I'm going to substitute for this right here, is going to be a negative VO sine, I guess I'm going to keep it as theta because I did it a second ago, and times t, which is going to be this guy right here. So we're going to stick this on the denominator, VO cosine of theta times x, right? We just brought them over there. We just replaced that t. Minus 1/2 g times x, now t squared, which is x squared over VO squared cosine squared of theta. And we know this goes to tangent of theta, and we know that these cancel out from each other, right? They divide out. So we could write out, let's stick the numbers in now that are going to be constants, right? So let's take y is equal to y naught, which is going to be 2.5, and it's going to be minus the tangent of 4 degrees, right? It's going to be the tangent of theta, so it's tangent of 4 degrees, times x, minus 1/2, and you notice we dealt with meters here, so we need g in terms of meters, and I know that the physics department likes to say that g is equal to 9.8 meters per second squared, but for whatever reason, we engineers like to put it 9.81 meters per second squared. We go 9.81. Now, this is a good thing to memorize. Students don't memorize it for some reason. I will always tell you if you ask me during an exam, but also note that, like in US units, we usually use 32.2 feet per second squared, right? So depending on what system of units, these are the two ones to memorize, 9.81 or 32.2. And again, I think the physics department also would just go 32. And it's not like they're wrong, but it's just kind of like, I don't know, tradition now at this point. 9.81. What we stick in for g, and then we have x squared, and we have v naught squared, and then cosine squared of 4 degrees. Now we could turn that into a value, and we can turn all of this into, whoop, no, I'll take that back. We could, we could turn all of that into a value. There you go. Okay, so here is rewriting the equation out again, but now with some values. For whatever reason, I kept the tangent of 4 as a thing. I guess I just didn't want to write out. I guess it might be a small decimal place or something. I don't know. X minus 4.929 is what that turns out to be. X squared over v naught squared, right? So what we could do is we could solve this equation for this. So we'll end up with v naught, and it's going to be the square root of, we're bringing a lot of stuff over, right, to the other, no, we're taking this right here. So it goes 4.929 times x squared divided by 2.5 minus the tangent of 4 degrees x minus y. Okay, so now we figure out what the velocity has to be in order, if we're given the parameters x and y, and x shows up in 2 spots here, and y, right? So this is really the initial velocity magnitude as a function of both x and y. All right, so we have 2 points that we have to deal with. We have this point is to get right over there. So we find what this value has to be able to get it over that, right? Given this angle and this height and start, we know that this thing has to have a magnitude. It's got to make it over the there. But also, it can't be so large as that it goes out of bounds right there. So that's the second point. So we go ahead and plug this in there, and I'm not going to put in the math into the thing. You can do this, 12.2 and 0.914. And if you put that in there, you get V naught is equal to 31.64 meters per second. And then if you put in this other coordinate right here, so we go at, and we go 18.6 and 0, we get V naught has to equal 37.71 meters per second. So this is the range of velocities that you need to get. Now, it's kind of amazing that a really good tennis player will just kind of have that feel of what that has to be, right? And they won't necessarily plan. They'll also be planning out what that angle is going to be. In this setup right here, that was a that was a given. If you weren't given the angle and the magnitude, it would be like an infinite amount of possible combinations that you could possibly do. But if we restrict this system to only having this this angle right here, here's the limited range that you could have for that ball to be into the service area. So I said that I was going to do it. I want to make sure that I point out to you that that we have. Okay, so this is in the class notes section, where you could download the notes, and you can also see some videos to give you other examples onto this thing. I will post this video, the links to this video and some of the other ones up here shortly. Also want to point out to the exam prep section, because our first exam is just going to cover classes 1, 2, 3, 4, and 5. So we're like right in the midpoint of where we're going to have like the exam stuff. So we have exam review stuff that's available. Like, you won't be able to see the solutions for a little while, but we have practice problems that you can go over, right? And so here's some more. Here is a Angry Birds practice problem. These are like old exam problems. So here's some projectile motion problems that you might want to go through. And then there's other problems in there too. But I've also put together this right here, which I believe is Hibbler. And you can see that we have various different types of problems that you might encounter. And as I mentioned or alluded to, finding the angle often requires sort of a little bit of a trick to find, and can be very frustrating. But we can have all different kinds of unknowns that we could put into one of these projectile motion problems, which will make it a lot more difficult than you might consider it at this stage right here, because it looks like we could just plug and chug, but a lot of times you actually have to think your way through to navigate to a solution strategy when doing one of these problems. So I'm going to go on to the next topic, which is relative motion.